Good morning, myself Sukhwinder Kaur from GPCG Patiala. Today I am here to teach you data representation, that is topic of computer architecture. So we will study introduction to data representation. Binary information is stored in memory or processor registers. Registers contain either data or control information, where data are numbers and other binary coded information. Control information is a bit or a group of bits used to specify the sequence of command signals. Data types found in the registers of a digital computer are numbers. Numbers used in the arithmetic computations, where letters of the alphabets used in the data processing. Other discrete symbols used for specific purposes. These symbols are like $sign, ampersand sign, and others. So now we will study fixed point representation. Computer must represent everything with zeros and ones, including sign of a number and the fixed floating point numbers. Binary decimal points. The position of the binary decimal point is needed to represent fractions, integers, or mixed integer fraction numbers. Fixed point numbers. The binary point is always fixed in one position. A binary point is the extreme left of the registers, that is fraction part, and represented as 0.xxx, where binary point in the extreme right of the register is the integer value. The binary point is not actually present, but the number stored in the register is treated as a fraction or as an integer. Now we will study integer representation. There are three types of integer representations: signed magnitude representation, signed ones complement representation, and signed twos complement representation. As we have seen in example, plus 14 and minus 14 is represented as 0, 0, 0, 0, 1, 1, 1 and 0. That is, 0 represent a positive value and the next 1 represent the negative value. So 0 represent plus sign and the 1 represent minus sign. That is, MSB, most significant bit of a string, represent sign value. The sign magnitude. Most significant bit of a value represent a sign. That is, 0 represent positive value and 1 represents negative value. For example, for a 3-bit set, most significant bit represent a sign bit, that is minus, and in this example 110 is a string and the most significant bit 1 represent minus and the 10 represent a value, that is 2. Ones complement. MSB as in sign magnitude complement all other bits. In ones complement method, we complement all the values. Complement means we inverse all the values, convert 0 to 1 and 1 to 0. Given a positive number, complement all bits to get negative equivalent. And in twos complement, first we complement, take ones complement of the string and then plus 1 to the ones complement. Now floating point representation. The floating point representation of a number has two parts. The first part is mantissa and the second part is exponent, where mantissa signed fixed point number and the exponent position of binary point, that is decimal. Scientific notation of this floating point representation is m into r raised to power e, where m is mantissa, r is radix, or we can say base of the number system, and e is the exponent of the number. Now we will study number systems. Basically in computer we have 4 number systems. That is, first is decimal number system, that is most commonly used. Second is binary number system and octal number system, and the last one is hexadecimal number system. Each number system has a base and collection of symbols. In decimal number system we have base 10 and the symbols are from 0 to 9, that is 0, 1, 2, 3 up to 9. And in binary number system we have base 2 and we have only 2 symbols, that is 0 and 1. All the values are represented by using 0 and 1. In octal number system we have base 8 and symbols 0 to 7. In hexadecimal number system we have base 16 and we have values from 0 to 9 and then from A to F. 0 to 9 are decimal values and A to F are alphanumeric values. A decimal number system is used by commonly by humans, and binary number system is used by a computer system. Here base is the number of symbols or number of digits or in any number system. We will compare representation of a value in 4 different number systems. Here in every number system 0 is represented by a 0, and in each again in each number system 1 is represented by a 1, and in decimal if it is value is 2, then in binary it is represented by 1 0, and in octal it is represented by 2, and in hexadecimal it is represented by 2. Then again up to 7 same representation is in decimal, same in octal, and same in hexadecimal, but in binary it is different. In binary it is represented in the form of 1 and 0 only. Again 8 to 15 representations of 4 number systems. Then up to 9 decimal and hexadecimal represents same values with same digits, and in octal system it different from decimal number system. After 7 octal is different from decimal and hexadecimal, and binary is same like 0 and 1's combination. Now we will talk about conversions among bases, like conversions in number systems. We can convert from each number system to any other number system, like decimal to octal number system, and again octal to decimal number system, decimal to binary and binary to decimal, binary to hexadecimal, hexadecimal to binary, hexa to octal, and octal to hexadecimal, and also from binary to octal, octal to binary number system, and decimal to hexadecimal, and hexadecimal to decimal number system. Now we will study all these conversions with examples and techniques. First example is suppose we have a value with base 10, that is 25. We will represent it in binary by 11001, that is base 2. Any base of any value represent the total number of digits in that number system. Then in octal number system we will represent this value by 31, and in hexadecimal number system we will represent this value by 19, that is 19. First we will study the basic, that is decimal to decimal conversion. This is just for an example that it will if we try to convert decimal to decimal, then it will return the same value, that is the input 125. That is 125 in decimal having base 10. We will take each digit separately 5 and multiply by 10 raised to power position of the bit, that is 5 into 10 raised to power 0, that is the position of MSB, that is 0. Then 2 into 10 raised to power 1, where 1 is the position of 2, that is second position. Then 1 into 10 raised to power 2, that is the position of least significant bit. Then we will multiply this by 10 raised to power n. N is the position of value, position of bit. Then all the results are added, and we will get the result as we have given the input 125, and the result is also 125. So this is only the technique to convert from number system to another number system. Now we will discuss binary to decimal conversion. In binary to decimal conversion, multiply each bit by 2 raised to power n, where n is the weight of the bit. The weight is the position of the bit starting from 0 on the right. Then add results. For example, we have a given string 101011 having base 2, and we will multiply each bit by 2 raised to power n. N is the position of a bit. We will start from most significant bit 1 into 2 raised to power 0, 1 into 2 raised to power 1, 0 into 2 raised to power 2, 1 into 2 raised to power 3, 0 into 2 raised to power 4, 1 into 2 raised to power 5. Then we will add all the results 1 plus 2 plus 0 plus 8 plus 0 plus 32. It will result 43. So the base of the result is 10, that is decimal number system. Now we will discuss octal to decimal number system. In this number system, the technique used is multiply each bit by 8 raised to power n, because we have the base 8, where n is the weight of the bit. The weight is the position of the bit starting from 0 on the right, that is we can say most significant bit of the string. Then add all results. For example, we have given value 724 having weight 8, having base 8. that is octal value. We want to convert it into decimal value, then we have to multiply each digit by 8 raised to power n. 4 into 8 raised to power 0, it becomes 4, and 2 into 8 raised to power 1, it becomes 16. 7 into 8 raised to power 2, it becomes 448. By adding 4, 16 and 448, by adding these three values, we will get 468. So the decimal equivalent of 724 is 468. Now we will discuss hexadecimal to decimal conversion. Technique for this is again same. Multiply each bit by 16 raised to power n. 16 is the base of hexadecimal number system, where n is the weight of the bit. The weight is the position of the bit starting from 0 on the right, that is again most significant bit of the string, and then add results. For example, we have a given string A, B, C having base 16. So we will multiply C by 16 raised to power 0, B into 16 raised to power 1, A into 16 raised to power 2, that is C into 16 raised to power 0 is equal to 12 into 1, that is 12, because C is represented by 12 in decimal number system. Again B is represented by 11. 11 into 16 raised to power 1 is equal to 176, and then A is represented by 10. 10 into 256 is equal to 2560. So by multiplying we get results 12, 176, 2560, and by adding these three results we will get 2748. That is a decimal value. So the equivalent decimal value of hexadecimal ABC string is the 2748. Now decimal to binary conversion. The technique for decimal binary conversion is divide by 2, keep track of the remainder, divide the value by 2, then keep track of the remainder. First remainder is bit 0, that is least significant bit of the result. Then second remainder is bit 0. For example, we have value 125 having base 10, and we want to convert it into a binary value. Divide 125 given value by 2. The result is 1 remainder and quotient is 62. Again divide 62 by 2, that is quotient 31, and the remainder is 0. Again the resulting quotient is divided by 2, and we will get quotient 1, and the quotient 15 and remainder is 1. Then again divide quotient by 2, that is quotient is 7 and remainder is 1. Again divided by 2, result is quotient is 3 and the remainder is 2. Sorry, remainder is 1. Again divided by 2, the result is 1 quotient and 1 is remainder. Again divided by 2, this division will go up to the quotient becomes 0. At last we have quotient is 0 and the remainder is 1. Now we will combine these values, these remainder values in a string. The result is 1 1 1 1 1 0 1 having base 2. So starting from the top is the top first remainder is the rightmost bit of our string. So we can start it from down counting. It is 1 1 1 1 1 0 1. So binary equivalent of 1 2 5 is equal to 1 1 1 1 1 0 1. Now next is octal to binary conversion. Convert each octal digit to 3-bit equivalent binary representation. For converting from octal to binary number system, first we have to convert each digit to a binary equivalent, then we will combine it. For example, we have a value 705 having base 8. We will convert it to binary by taking binary values of each digit. For example, 7's binary value is 1 1 1, and 0's binary value is 0 0 0. 5's value is 1 0 1. We will represent each digit of a octal number system by 3 bits, and then combine these values, it will get octal in binary number, that is 705 having base 8 is equal to 111000101 having base 2. Now we will study how to convert a hexadecimal number to a binary number system. Technique for this is convert each hexadecimal digit to a 4-bit equivalent binary representation. As we have studied in from octal to binary, we have converted each octal digit to a 3-bit equivalent binary representation, but in hexadecimal we will convert each hexadecimal digit to a 4-bit equivalent binary number. We have example 10AF having base 16, and we have to find what is the value in binary. First we will take binary values of each digit. For example, for 1 it is 0001, for 0 it is 0000, for A the code is 1010, and for F the code is 1111. All these codes we have studied in the tables previously in second or third slide. Then we will combine these values, and the result will be 10AF having base 16 will be equivalent to 0001 0000 1010 1111 in binary number system having base 2. Now we will study decimal to octal number system, where decimal number system have base 10 and octal number system have base 8. The technique to do this conversion is, first step is divide by 8. Keep track of remainder. In this conversion we will take example 1 2 3 4 having base 10, and we will convert it into an value having base 8. 8 is an octal number system. Then we have the given value 1 2 3 4, so we will divide it by 8, and the result is 154 is our quotient and 2 is our remainder. Again the quotient will be divided by 8, and the result from this division is 19 is our quotient and 2 is remainder. Again we will divide it by 8, and the result is 2 quotient and 3 is our remainder. Again we will divide it by 8, where division by dividing result quotient is 0 and the remainder is 2. So we will divide up to the quotient will get 0, and the result will be 1 2 3 4 having base 10 will be equivalent to 2 3 2 2 8, and we will count from top is the rightmost bit of the resulting value, as the arrow shows the topmost 2 represent the rightmost bit of the resulting value, that is an octal number system. Now how to convert a decimal to hexadecimal. Again the technique is same, but the difference is in only base. Divide by 16, the value we want to convert, divide that value by 16, keep track of the remainder. For example, if we have 1 2 3 4, that is the same we have taken in the previous example, that is a decimal value having base 10, then it is we have to convert it into base 16 value, that is hexadecimal value, in that 16 digits available. That is again the same process. We will divide 1 2 3 4 by 16. The result will be 77 quotient and the 2 remainder. Again we will divide 77 by 16. We will get a result 4 as quotient and 13 as remainder. Then we will again divide it by 16 because we have not get quotient as 0 yet. Then 4 is divided by 16, and result quotient is 0 and remainder is 4. So we will divide up to quotient is 0. So it is 0, then stop dividing and then count or keep track of remainder. Then 1 2 3 4 having decimal base 10 decimal number system will be equivalent to 4D2 having 16 base, that is hexadecimal number system. Here 2 and 4 both are digits of hexadecimal number system, where 13 is not the digit or symbol of hexadecimal number system. So we will convert 13 to the hexadecimal number system, that is 13 is equivalent to D. So we will replace 13 by D and the resulting string will be 4D2, that is a hexadecimal equivalent of a decimal number system, that is 1 2 3 4. Now we will study how to convert binary to octal number system, where binary is a number system having base 2 and the octal is a number system having base 8. In binary we have only 2 bits 0 and 1, and in octal we have 8 bits from 0 to 7, that is 0 1 2 3 4 5 6 and 7. The technique for this is group bits in threes starting on right, convert to octal digits. For example, we have a given string 1011010111 having base 2 and we want to convert it into an octal number system. First, make groups starting from right of 3 bits. First group will be from rightmost 111, then second will be 010, third will be 011 and the next will be 1. We can add 2 zeros with the last group, and the first from right first group will be represented as 7 in decimal, and second group will be represented as 2 in decimal, and the third group will be represented as 3 in decimal, and the last group will be represented as 1 in decimal. So our resulting value is 1327, that is the string binary string 101101101111 will be represented as 1327 in octal number system. Next conversion is binary to hexadecimal conversion. Technique for this conversion is group bits into fours starting from right. As we have hexadecimal having base 8, base 16, so 2 raised to power 4 is always equal to 16. So we will group these values, these bits with 4 bits and then convert to hexadecimal digits. For example, we have given value 1010111011 having base 2, that is binary, and then we have to convert it into hexadecimal, that is base 16. First we will make groups starting from rightmost values. First group will be, we will make groups of 4 bits. First group will be 1011, second group will be 1011 and the third group is 10. We can add 2 zeros to the left side of the last group. Then the first group will be represented as B in hexadecimal, and the second group will also be represented as B in the hexadecimal number system, and the last group will be represented as 2 in hexadecimal number system. And then the equivalent value for binary number system, that binary value, that is 1010111011 is 2BB, that is hexadecimal number system having base 16. Now conversion from octal to hexadecimal number system. The technique is very easy for this to use binary as intermediary. First we will convert octal to binary number system, then we will convert that binary number system to hexadecimal number system. Now first we should know how to convert octal to binary, then how from binary to hexadecimal. For example, we have 1076 having base 8 and we want to convert it to hexadecimal number having base 16. For example, we have 1076. We will take binary values for all these digits. For 6 we have starting from rightmost. For 6 we have 110, and for 7 we have binary value 111, and for 0 we have binary value 000, and for 1 again we have binary value 1, but we will add two zeros to left position of the bit, that is then the code becomes 001, and we will group these bit groups. We'll combine these groups and then again group these bits in four bits. First group will be 1110, and the second group will be 0011, and the third group will be 0010. So the code for first group is E, starting from rightmost, and the code for second group is 3, and the code for third group is 2. So the result is, for 1076 having base 8 value and octal value, the equivalent hexadecimal value is 23E, that is base 16. Now we will study how to convert an hexadecimal number system to octal number system. It is very easy. We will use the technique, use binary as an intermediary. Here we will convert first hexadecimal to binary number system, then binary number system to octal number system. So we should know how to convert an hexadecimal to binary and how to convert binary to octal number system. For example, we have 1F0C. This is an hexadecimal number having base 16, and we want to convert it to a number system and value having base 8, that is octal number system. Start from rightmost, that is C. C will be represented as 1100 in binary, and 0 will be represented as 0000 in binary. Then F will be represented as 1111. Then 1 will be represented as 0001. Here we take group of 4s, as I have already teach that group of number of bits in a group is depends upon the base of the number system. We have 16 base in hexadecimal, and 2 raised to power n is equal to 16. If we will find n, then n is equal to 4. 2 raised to power 4 is equal to 16. So we will make group of 4 bits. Then again we will make grouping, as we have studied, having octal number system having base 8. So 2 raised to power n is equal to 8. If we will solve this equation, the n will be 3. It means 2 raised to power 3 is equal to 8. So we will group these bits into these string into group of 3 bits. Here for first group from rightmost 100, we have value 4, that is octal representation of a binary number is 4. For 100 is 4. For second group 001, it is 1, and for third group, that is 100, is 4. For next group, that is 111, that is 7. For next group, that is 001, it is 1, and we will discard the last bit, that is 0. No need to read this bit, as we have separated these groups by a line. So the result will be 17414. So the input is our question is how to convert from hexadecimal to octal number system. So we have 1F0C is in hexadecimal, and the equivalent octal number for this hexadecimal is 17414. Now we will study binary arithmetics. How to add binary numbers, how to multiply binary numbers. So first we will study binary addition. 2-bit values. First we will study rules of binary addition. We have 2 values A and B, and we have 4 possibilities of combinations of these values. We have 2 base for binary values, 0 and 1, base 2, and 2 raised to power 2 is equal to 4. 2 raised to power 2 is equal to 4. It makes that if we have any number system with having base n, we will have possible combinations of those multiplications is 4, that is 2 raised to power n is equal to 4, means 2 raised to power 2 is equal to 4. 4 is the possible combinations of a and b or values. If a is equal to 0 and b is equal to 0, then the result of a plus b always will be 0. These are the rules for binary addition. Then for a is equal to 0 and b is equal to 1, the result will be 1. And for a is equal to 1, b is equal to 0, the result will be 1. Again for a is equal to 1, b is equal to 1, the result will be 1 0. Here 1 0 represents 2. First result is 0 represents 0. Second and third are same results, 1 1, these represents 1. And the last result, that is 1 0, it represent a 2 decimal value. 1 0 in binary is equivalent to 2 in decimal. Now we will